Now, estimation of relative acid or base strength. So, ionization constant Ka indicates relative strength of the acid or a base. An acid with Ka of 1 into 10 raised to minus 3 is a stronger acid which is more ionized than one with Ka of 1 into 10 raised to minus 5. Same goes with the base. A base with Ka of 1 into 10 raised to minus 7 is weaker, it is less ionized than one with Ka 1 into 10 minus 9. Ionization of weak acid, acetic acid pKa is 4.6, is as follows. And these are the charts wherein we get the relative acidity and basicity strength, wherein we are going to select the molecules for doing the structural modifications. Few examples of the aliphatic amines with the examples of its pKa and with the structural features also. Now coming towards the next thing wherein we are going to study about the effect of pH on drug absorptions. An acidic drug absorbs better in acidic media and basic drug absorbs better in basic media. So acidic drug like aspirin are better absorbed in stomach and basic drugs like diazepam are better absorbed in intestine. So acidic drug better excreted in basic media, whereas basic drugs are excreted in acidic media. In case of acidic drug poisoning, alkalization is done to promote excretion of the drug, and in case of basic drug poisoning, acidification is done to promote excretion of the drugs. Importance of pH and drug pK. So degree of ionization depends on pK of the drug. pK, value of drug pH when the concentration of ionized and non-ionized form is equal. If pK of drug is equal to pH of the media, then 50% of the drugs are ionized and 50% are non-ionized. So based on the nature of the drug, the concentration and the pH, it tells us about what will be the ionized molecule and what will be the non-ionized molecule. This particular slide explains us about the basic drugs with increasingly ionized form and the pKa values, and acidic drugs with increasingly ionized forms with the pKa value of the molecules. Now, importance of ionization. An ionized form of drug can partition across biological membranes as the unionized form is lipophilic. Ionized form tends to be more water soluble as it is important for drug administration and distribution in plasma. Lower the pH with respect to pKa, greater will be the fraction of protonated drug which may be charged or uncharged. Weak acids are more lipid soluble because they are uncharged, and hence this form passes through biological membranes more rapidly. Acidic pH provides a proton to weak acids to form uncharged species. Similarly, alkaline pH will cause weak bases to lose a proton to form uncharged species. Next comes the redox potential. Oxidation reduction potential is defined as quantitative expression of the tendency that a compound has to give or receive electrons. The correlation between redox potential and biological activity can be drawn for the compound of very similar structure and properties. Redox potential is calculated from the following equation. E is equal to E0 plus 0.0592 by N into log concentration of reductants by concentration of oxidants. The example is riboflavin analogs. So biological activity of riboflavin is due to E, which is minus 0.185 volts. And the optimum bacteriostatic activity of the next example in quinones is associated with the redox potential, which is plus 0.03 volt when tested against Staphylococcus aureus. Next comes about the protein binding. So reversible binding of proteins with non-specific and non-functional site on the body proteins without showing any biological action or effect is called as protein binding. So protein pan drug, it gives a protein drug complex. Depending on whether the drug is a weak or strong acid, base, or is neutral, it can bind to single blood proteins to multiple proteins like serum albumin, acid glycoprotein, or lipoproteins. The most significant protein involved in the binding of drug is albumin, which comprises more than half of the blood proteins. So protein binding values are normally given as percentage of total plasma concentration that is bound to all plasmas. Next is the surfactant activity, or we call it a surface activity. So surfactant is defined as a material that reduces the surface tension of water at very low concentration. Surface active agent affect drug absorption, which depends on chemical nature of surfactant, its concentration, and its effect on biological membrane and formation of micelles. In lower concentration of surfactant enhances the rate of absorption because amplifies reduces the surface tension and better absorption. In higher concentration, surfactants reduce the rate of absorption. Applications. The antihelmintic activity of hexyl resorcinol was studied by the surface activity, bactericidal activity of cationic quaternary ammonium compounds, bactericidal activity of aliphatic alcohol, disinfectant actions of phenol and cresols, and bile salt solutions of approximately physiological concentration greatly enhances the dissolution rate of poorly water-soluble drugs like glyceofulvin, hexasterol by micellar solubilization effect. Then comes the stereochemistry of a drug. So stereochemical aspect is to be critically studied because the binding of a drug specifically to the receptor depends on arrangement of atoms and groups in spaces. So stereochemistry is arrangement of atoms and groups in space. And we are going to see three parameters here when we study stereochemistry: optical isomerism, geometrical isomerism, and conformational isomerism. So these three parameters are studied for a drug to help to determine quantitatively the mixture with same groups or different groups. And this study helps to determine whether the compound is asymmetric or symmetric and whether it is active or inactive in nature. So isomerism helps us to confirm the structure further by QSAR studies, and these QSAR studies explains the drugs and the structure to get a tailored compound. So when we are going to study stereochemistry, we need to understand how stereochemistry is going to play an important role. So stereochemistry plays a major role in pharmacological properties because any change in stereospecificity of drug will affect its pharmacological activity. And the isomeric pairs have different physical properties like log-P and pK, thus they differ in pharmacological activity. So isomers which have same bond connectivity but different arrangement of groups or atoms in the space are termed as stereoisomers. Conformational isomers, different arrangement of atoms that can be converted into one another by rotation about single bonds are called conformations. Rotation about bonds allows into conversion of coformers, right? So classical example is of acetylcholine, which exists in different conformation. So it is in staggered and eclipsed and gotch and fully eclipsed form. The conformation totally explains about the binding of the molecule to the site, right? So what is going inside and what is going outside into the receptor? So best it is being explained by the 2-point and 3-point attachment of same receptors. Example, adrenaline in levo form exhibit 3-point attachment and adrenaline in dextro form exhibits 2-point attachment. This example is important to study the potency of drug and the compounds were screened to achieve similar activity, which was found with dihydroadrenalines, which proved the hypothesis of 3-point attachment and 2-point attachment, which in therefore for all drugs helps in crossing the blood-brain barrier. Now, the next example for optical isomerism, we can also quote about the S-methyl dopa, which is an active antihypertensive, whereas R is inactive. And third example which we can quote is amphetamine, which is 3 to 4 times more stimulant. S is more stimulant than the R1, right? Next comes geometrical isomerism. So isomerism arises out of restricted rotations around C double bond C or the rigid cyclic structure. Two geometrical isomers have different activities, and this is being explained by best example to explain this particular concept is by using the steroids. So diethyl stilbestrol, which is an isomer, a trans is more active than the cis form. So these arises due to free rotation of group around carbon-carbon bond at 360 degree. Next example of acetylcholine, it has a Newman projection, which makes it an active agent, and ester group is important for the activity. Hence, it is an acetylcholine esterase binder. When the molecules are exhibiting in two forms, so one we will say a staggered form. So it is responsible for when acetylcholine is in staggered form, it gives activity towards muscarinic receptor. And this particular example explains about the minimum energy consumption, which has proved the conformation of compound which are totally related to the activity of degrees of rotation. So staggered form has two carbon atoms which are not visible, but all the second carbon atom will have conformation, and we are able to see the protecting groups to have an active feed into the receptor. Active fit into the receptor, right? Eclipsed form will be devoid of the activity, and hence acetylcholine will have only muscarinic effect in staggered form, whereas the nicotinic effect in Gauge conformation. So in Gauge conformation, it will have affinity towards the nicotinic receptor. Hence, it will be called as a potent active fit towards nicotinic agent. And this has a maximum energy and is studied as a model for conformation in computational relationship. Therefore, rotation of group in a drug molecule has an open chain of atom which are joined by single bond which have freedom of existing in all possible conformation due to free rotation of C double bond C. Even we can explain the concept of fully eclipsed. So drug molecule with which have an open chain of atom joins by single bond and have freedom of existing in all possible conformation due to free rotation of carbon-carbon bond. Now the concept of bioisoterism is going to help us to explain about the use of several bioisosters which are going to help the molecule to have desired pharmacological activity. So what bioisoterism is? Bioisoterism is defined as compounds or groups that possess near or equal molecular shape and volumes, approximately the same distribution of electron, and which will exhibit similar physical properties. So when we want to classify these bioisosters, they are classified into two. One is classical and second is non-classical. So bioisoterism, before that, we will see how this particular tool is being used for drug design. So bioisoterism is a tool for drug design, which was explained by Langmuir, and who observed the similarity in physical and chemical properties of atoms, groups, radicals, which have similar electronic structure. And he defined these mechanism, and he defined these as isoterism, which further was known as bioisoterism when isosters were studied for its potency. So isosters are atoms or groups which have same number and arrangement of electrons in outer shell of any such atom which shares same number of electrons. These are termed as isosters. So the best example are N2CO. Isosters have same physical properties and same chemical properties too. Hence, they are classified into Medichem as classical and non-classical. And this classification was given by Burgess, wherein he explained bioisoterism with few of the examples, right? So bioisoterism was further extended to study the substitution patterns which are going to change the physical and chemical property, and then with broad examples for the biological action. So concept of isoster was invented and was being studied to improve the biological actions. So when we come to bioisosters, we have univalent, we have divalent, and we have tetravalent bioisosters, which really play a role in the biological action of the molecule, in modification of the biological actions. So with this, we will study how application of classical bioisosters was done by replacing of NH2 group by a CH3 group. An example was carbutamide, wherein NH2 was there, and in tolbutamide, CH3 was there. Second example is in replacement of OH and SH, wherein guanine and thioguanine had shown an important role. So few of the examples which explains about this. And non-classical bioisosters, they exhibit specific properties or characteristics. So they are having electronic properties, exhibit electronic properties. They affect the physicochemical properties, spatial arrangement, and functional moiety of the biologicals. So this particular concept of how biologically biological activity of the molecules is being affected by physicochemical parameters is being studied by all the parameters what we have seen in this lecture. So I hope you all have understood the concept of how important it is to design a molecule when it comes towards the application part to understand the mechanism of action, right? So in a nutshell, we need to understand the concept of physicochemical changes. What we need to do is to understand the basis of mechanism of action. It makes us more clarified towards the therapeutic uses and adverse drug reactions. It helps the um, medicinal chemists to understand the principles of organic chemistry for synthesizing drugs, and it also correlates with the route of synthesis and influence of substances which are going to improve the biological action. So in a nutshell, when we have studied this particular chapter, we have touched upon various aspects which we should learn while studying the drugs to improve the biological action. So this was the first lecture for as an introduction towards medicinal chemistry, how medicinal chemistry is interlinked with all other branches, and how physical and chemical properties are going to affect the biological action of the drug. So this completes the end of the chapter. We will see the next chapter of diuretics in the next lecture.